When discussing discharges in rivers, whether we're talking about water or sediment, we have a principle that we call continuity. And that's an assumption that says everything that goes in must come out. And the reason that we have that is because it's useful and it's usually true. And I'm going to explain it really shortly. So let's say that we have this little box that's a section of river. And we have some water that's going in, Q in, and some water that's coming out, Q out. So if Q in is greater than Q out, then the surface of the water is going to rise. If Q out is greater than Q in, the surface of the water is going to fall. But in actuality, in rivers, all this flow is going at around 1 meter per second. And while the river's surface is rising and falling, maybe a little bit, it's going more like fractions of millimeters per second, if even that. And oftentimes the water level stays basically the same over the course of many days. And therefore, what we can say is that any storage or release inside this reach of river is basically zero. And because of that, we know that if there's no mass gained or lost in here, that everything that goes in, by conservation of mass, also has to leave. So that might be kind of an obvious concept, but it becomes really useful. So what I'm going to do is sketch out an example of a rectangular channel. And in this channel, the flow is going to be coming towards us, the observer, like this. The channel has a width, b. If you have trouble remembering that, just think of the British and breadth. The thickness of that flow is h, so that's going to be the height of the water inside the channel. And the water is going to be moving at some velocity, u bar, towards the viewer, so towards us. And if it's a rectangular channel and we have all of these numbers down, what we know then is that Q, which is the discharge, is just going to be equal to the width times the depth times the mean velocity. And we can just check that with units really quickly. So width is going to have units of meters, right, like length. Height, also meters. Velocity, meters per second. And so here we are, meters, meters, meters. That's 3 meters. So meters cubed per second. And so that this gives us the volumetric discharge. Which I often just call the discharge. So let's do a little thought experiment right now, shall we? So let's pretend that we're looking down on this landscape, and there is a narrow gorge that empties out into this wide embayment. And as the water is moving through this narrow gorge and into this wide embayment, you might think that the flow is going to spread out a little bit. So I'm going to draw two cross sections here, and I'll actually take advantage of having some different colors. So this one up here, let me see if I can make there we are, better straight line, is going to be from A to A prime. And this one out here is going to be from B to B prime. So the first cross section is going to have flow that is quite deep and narrow compared to the other one. It is still going to be a little bit vertically exaggerated. So what I'm going to say is that this flow is 4 meters deep times 10 meters wide. And it's going from A to A prime. And it's coming towards us at 2 meters per second. Now, the second one is a flow that's much wider. And we can see from watching material move at the surface and making some measurements that this flow is moving at 0.5 meters per second, and that the width is about 5 times the other one. So we're going to say the width is about 50 meters. And from that, we're going to figure out how deep that flow must be. Now, it's more often that you'd actually know the depth because that's easy to measure and try to get the velocity out of this, but we're just going to solve it a different way, shall we? So Starting out here, we have 10 meters times 4 meters times 2 meters per second. So 1 times 4 times 2 is 8. With a 10, that's going to be 80 cubic meters per second. Over here, we have 50 meters, and then we have half of a meter per second. So what we have is then Q is going to equal 80 cubic meters per second is going to equal 50 meters times h, which we don't know, times 0.5 meters per second. So 50 times 0.5 is 25 meters. And 25 meters squared per second times h. And so if I want to bring this 25 meters squared per second over to the left-hand side, I can do that. And so I have 80 here, I have 25 here, and I'm going to say that 80 over 25 is approximately, to first order, 3 meters. And so what that means here is that we have a flow that is 3 meters high. So there we go. That's the concept that we have right here. So this is continuity, and you can use it to try to understand what relationships between different flow and different zones in the river might be. And one last piece about continuity is that it's more than just water. So I'll put this in gray because it works for sediment too. And so as you might imagine, that if this flow is really deep, it's going to be able to carry a lot of water and a lot of sediment with that water. And that sediment is going to be moved along by this high shear stress that this flow is placing on its bed. But as the flow becomes shallower and expands out here, it's actually going to be significantly decreasing its capability of carrying sediment. And so you might expect that we'll have deposition here. And we can look into that more when we talk more specifically about sediment transport. But this is a case in which continuity is broken. We have stuff going in that is not coming out. And that is actually a very important tool as well. So to summarize and just make sure that we back this all up, get back to the beginning. If we have about the same amount of stuff coming in as going out, then we have continuity. And what that means is that if we're looking at discharge, we can then use continuity to say that the same discharge must be going through different cross-sections, and therefore we can use it to solve for unknown values when trying to think about how much water is going through one chunk of a river or one cross-section of a river, to actually use the formal term, versus another.